Good morning, ladies and gentlemen. Nice to feel your presence. So today there will be problem solving session, and that will be devoted to presentation of Hristo Barakov. He will tell us about the topic which is related to what we are dealing on the lectures now. So classical field theory oscillations and right, but that will be in a little bit fancy way. It will be other way around, because we will talk about magnets, I believe. All right, Christos, sir, if you could switch on, share your screen.
Okay, I hope everyone can see my screen.
Yes, it is.
Hear me?
Perfect.
Okay, so as Yuli said, we're going to talk about oscillations of magnetizations in a ferromagnet, and we're going to derive magnons in the end. So as an outline of the talk, first we're going to look at this ferromagnet in an external magnetic field. And in this, we're going to be interested in the energy of the magnetization, and we're going to derive the Hamiltonian in generalized coordinates. Later on, we'll move to the case where there is no external field, but the magnetization will be space dependent. And again, in this case, we're going to look at the Hamiltonian of the system where fluctuations are present, and rewrite those fluctuations in terms of Fourier components in order to derive our magnons. Okay, so part one, we have a ferromagnet in an external magnetic field. This external magnetic field is along the z direction. And we concentrate on the case where there is uniform magnetization. The magnetization is not spatial. There is no spatial dependence of the magnetization. And we have the constraint that the magnetization is normalized to 1. Okay, so what we do is we assume that there are small deviations from this direction, in this case from z direction, and we have to find the energy, which is written in the usual case. We have, of course, the magnetization times the magnetic field, and because it's along the z direction, we simply have the strength of the magnetic field along the z direction times the magnetization along the z. Now, because we have, later we'll assume small deviations from this z direction, we immediately write the energy in the following form. So we have the square root of 1 minus mx squared minus my squared, and this comes from the normalization. So we express the z component. Okay, and of course we assume that the deviations are small, so we can expand the square root to obtain the following expression. We have minus b, just a constant, and we see that to first order we have mx squared plus my squared. Now, in order to derive to find the equations, to find the Hamiltonian in generalized coordinates, it is said that the equations of motions for m read in the following way. What we want here is simply to make an analogy between those coordinates mx and my with the generalized coordinates n momenta. So here they are, the generalized coordinate momenta. I will assume that, okay, Q is equal to mx and P is equal to my. If we simply replace those in the Hamiltonian, then the Hamiltonian will have the following form, something very reminiscent about an oscillator. So we have P divided by 2, and then P squared plus Q squared. I think it's easy to see how this comes from, just replacement of the variables. We can perform just quickly correctness check, meaning that in classical mechanics, uh, we have in the Hamiltonian formalism, we can take the derivative of Q, for example, which the time derivative, sorry, this is the time derivative of Q. And then those are the Hamiltonian equations. We have that the time derivative of Q will be the derivative of H, the Hamiltonian, with respect to the generalized momenta P. And we have the conjugate equation, so to say, where the generalized moment, the time derivative of the generalized momenta is equal to minus the derivative of the Hamiltonian with respect to the generalized coordinate. Simply performing two derivatives, we find the following expressions for Q dot and P dot. And of course, bear in mind that we have analogously expressed mx as a function of q and my as a function of p. Then we find the generalized, again, we find the generalized equations of the equations of motion for the magnetization. Okay. I don't know if there are any questions for now, so I'll move on. In part two, what we're going to deal with is, again, a ferromagnet, but this time there will be no magnetic field that is applied to the ferromagnet. So here the external field is 0. On the other hand, the magnetization will be spatially dependent, so it's not a uniform magnetization anymore. It depends on the coordinates, and this will mean that the energy now would be a functional of this field M of R. Okay. Of course, the minimum of this energy will be given for a uniform magnetization. But what we're interested is what will happen if there are fluctuations of this magnetization, so spatial fluctuations of this magnetization. The energy, of course, should be invariant under rotation of M, because if we take the ferromagnet and we rotate it, the energy does not change, even if there are fluctuations. So that would more or less lead us to a following form of the energy. So how this is found is a simple expansion of the energy with respect to small deviations of M, right? How can one explain this? So we have some sort of a constant for now. Alpha and beta are just the 3 directions. We have an integration over all spatial coordinates. And as you can see, we have first derivative with respect to first derivative of the magnetization components with respect to the spatial coordinates. And the square comes from the fact that, yeah, the energy should be invariant under rotation. Okay. So there is a question, why can we take the derivative of M in respect to R inside E? So the first, it's an expansion to lowest order with respect, okay, so the minimum of the energy is for uniform magnetization. And then, so this is the 0th order, and then the first order, right? The first order expansion will be just the derivative with respect to the derivative of the magnetization with respect to the spatial coordinates. Here, if maybe the confusion is that I have written E as a function of the derivative, but yeah, it's just one needs to expand it. So there will be, of course, not only a single derivative, but high order derivatives, but we look at the lowest order. Okay. We have the following Hamiltonian now. And again, we're going to perform the same approximation, meaning that we're going to look at deviations from the z direction. So we're going to assume that there are fluctuations. We can choose any direction in this case. It does not matter. But we're going to choose again the z direction, and we're going to look at what are the fluctuations around this direction. So I have skipped several steps here. Let me remind you here, alpha and beta are x, y, and z. So what we have here is, in principle here, in this expression, sorry for this, need to move the chat. In this expression, one would have also the z component, right? If you look at the first equation, then it will follow that you also have the derivative of the z component with respect to all spatial coordinates are here beta. Okay, and this will also be squared. So what we have done from the first line to the second line is actually we have neglected those, because we can again express mz to first order in the following manner here. So we can replace this in mz and then take the derivatives again. Take the derivative with respect to r beta and square it. And what we'll find is actually we'll find terms that are proportional to not the first derivative to the second power, but actually the first derivative to the fourth power, which in this case can be neglected. And that's how we end up with the form that is written here. Okay. So once we have the form of the Hamiltonian, what we'll try again is to put it in the form of the harmonic oscillator. And for this, it's very intuitive to introduce new variables. And those variables will be, again, very analogously to what we have seen for the quantum harmonic oscillator. We have m plus minus, which will be a linear combination. So again, mx plus minus y and y. Okay. Such that, of course, they have also the following relationship, or the inverse relationship between mx, my, and m plus m minus. So our next step is to replace to express mx and my as a function of the new coordinates. So replace those in the Hamiltonian we have just derived. I remind you, it's the Hamiltonian. In this case, so there is a question about, are the m plus and m minus here operators, or just two new variables? In this case, we still consider them to be two new variables or fields. So just two new variables. And what do we do? Yeah, simply replace them. We'll have a little bit of a long expression, but pretty easy to follow. As you can see, mx is here. So this is mx for the first one, and the second one So let me note it. So mx in green, and then in blue, this is my expression just expanded by replacing the Hamiltonian. So as you can see, some terms will disappear. All the terms, all cross terms will stay, and the terms that are squared will disappear, because this one comes with a plus, this one comes with a minus, plus, minus. And this one comes with a plus, and this comes with a plus from this minus sign. So in total, you would have the following expression. In these new variables, we have the new variables m plus and m minus, and the derivatives with respect to the spatial coordinates. Okay. I will move on if there are no more questions about this, of course. Now, our next step is, because as was already discussed, those are new fields. So we would introduce the Fourier decomposition of this field. Again, what do we have? Just the discrete Fourier transform of the field. We have some volume here, volume, and the sum over all modes. Here, mk and mk star now are just coefficients still. Okay, the R dependence is taken into the exponential, and our next step would be to introduce those decompositions into the Hamiltonian we have just found. Yes, sorry, I forgot. At first place, we need to calculate the derivatives, but that's immediate in case of when we're working with Fourier decomposition, because the derivatives will be transformed in simple multiplications by this, now what is called the spatial frequency, or k beta. Our next step would be, once we have the derivatives of the fields that are in Fourier space, we simply replace them in the Hamiltonian we have found. So here they are. Here's the Hamiltonian. Again, plus, and this is the m minus field in Fourier space. Notice that here, k and k prime are different. It's they're not the same, so you should take a different index. Then we further proceed to some simplifications. We combine, simply put all coefficients in front of the integral, what does not depend on r. Okay, those were the spatial frequencies and the components of the Fourier decomposition. And we have, at the end of this expression, we have the following integral. I hope that everyone knows that this integral is equal to this. So it's equal to the volume times, that's one of the definitions in of the Dirac delta function, of course. And then once we have this delta function of kk prime, we can sum over one of the sums. So k would be equal to k prime, and we find the following. So mk star, mk, the sum over k, and what we have here is the sum over beta of as you can see, the components of k squared. So this would be, this is the norm of the vector k, just written explicitly. Okay, yes, here, sorry for those two steps, but yeah, here we have k squared, the sum over k being a vector, and again, mk star and mk. Here I've just written out explicitly the integral in a very bad manner, but this is in principle the delta function of kk prime. And so finally, yeah, we have obtained this Hamiltonian as a function of the components mk star and mk. So what does this Hamiltonian mean? We can see that we can write the Hamiltonian as the sum, the Hamiltonian of the fluctuations as the sum over the modes, right? So this K is the sum over all possible modes. And yeah, mk indicates the strength of the mode, but it is pretty easy for one to generalize those k star and mk just to say that those are now operators, or to quantize the fields, and they would become yeah, as you could easily just quantize the fields and rename them as for example, a dagger k and ak. And those will be our the fluctuations of the field can be understood also as magnons or particles, quantum particles in this case. And one can also look at the coefficient here in front, right? We have c, some constant, k squared. In principle, we would like to put the Hamiltonian in the form of h bar times, right, just a dagger a. So we can identify some kind of, not some kind, but we can identify a frequency in this case, and the frequency, this frequency is written right here. So this will be the frequency of oscillations. So with this, I would like to conclude and thank you for your attention. Are there any questions now? I don't see any. There is a question where did the beta go? So here is where beta goes. If this is where beta disappears, the modes do not depend on beta. The only thing that depends on beta is k, and the sum here, the sum over beta of k beta squared is just the norm of k. So this is k squared here, because this would write as kx squared plus all the rest, and this is just the norm of k. You're welcome.
Could you go one slide forward to the frequency, please?
This one?
Yeah, great. Thank you. Yeah, I'm just trying to figure out the units whether they match.
Well, you don't know the units of c, no, right?
Oh, C. Oh, right. Yeah. C's. I thought that C was the speed of light here, but then that makes sense. If C is just yeah, clear.
So I guess if there are no more questions, then I'll give the floor to Yuli. Or are there any more questions? Yeah. You can unmute yourself and ask it if it takes too long to write. The motivation is what people call to quantize the fields. So we go from just simply classical fields to very often you would see this. You go from a classical field to a quantum field just by quantizing variables by operators. It is done. It is done very often. So that's the motivation, to go from classical to quantum description of the problem. And you can see it as we have somehow looked at classical fluctuations of the field and what happens with magnetization. So one can imagine just magnetization that fluctuates, and then this also can be seen as just magnons, or the creation and annihilation of magnons. Okay, so I'll stop sharing now.
All right, thank you, Christoph. It was a little bit short, but anyway, I guess you told us what we wanted to hear. So it was, in fact, classical physics in a way which we did in a previous lecture a week ago, right? What was fun, if you have noticed, we have previously derived these magnons and the magnon spectrum in a quantum way, starting from microscopic model and doing manipulation with creation and annihilation operators. But since the result is a field, one can also do the same calculation on a classical level, and then quantize these oscillations of the field. We'll quantize on Monday, and right to get a consistent picture of quantum field. That's one can do with many systems. Magnons have been just taken as an example, just to kind of make you confident that you also are able to quantize any field to find correspondence between classical description of the field and quantum. And that can work, as you have seen, in both ways. Very good. We have still plenty of time. So what we can do, I can answer your questions about the course if they concern organization of the course or content of the course, or whatever related to advanced quantum mechanics. I'm here. I can try to answer questions. Of course, you can formulate a question which I cannot answer, but well, I will do my best. So if anything has been accumulated, is our schedule available for when groups have to present their respective problems? Yes, perhaps I still have not explained carefully how scheduling of presentation works. It works as follows. I pick up some date, usually 2 or 3 weeks in advance. All right. Me, not you, me. And I looked through the list of the groups and sent invitations to the group leaders. Right? Group leaders respond. Some agree, some say they have better things to do than present advanced quantum mechanics. That I perfectly understand. So I will try to fill time slots for a certain date. Some people have preferences about the dates. Yeah, I would love to hear these preferences, but I cannot promise, given the system, that you will be scheduled on this day. Right? So that's why there is no schedule, because the schedule is formed dynamically. Again, I pick up some date which is convenient to me, convenient to um, most of people. So that goes like this. But anyway, if you really want some date, you can negotiate it with me. For larger groups that are presenting, are you expecting everyone to speak for roughly even amounts of time? Or is it okay if some people do more of the talking? Yeah, I guess it's just written in FAQ. It is impossible for 5 people to talk because switching between the screens or whatever would take most time of the presentation. So we expect a single presenter or 2 presenters. Or one can assign the third person to answer the questions. So I guess generally 2 presenters is optimal number. And it's up to you how do you divide the labor in your group. It's, I would say, intimate. So perhaps presenter could not do anything, but just present, and the rest would make presentation sheets for him. Okay. Also, perhaps you have noticed the presentations, in fact, are very different. The presentation topics are various, and the complexity of presentation are different. We did not make an effort to make it as a military academy to have kind of all uniform. Rather, since the world around us, life gives us problems of different complexity. Um, yeah, one shall accept this. It might seem that some students work more and some students work less. Yeah, but that's also kind of real life. That's why one can choose the presentation topic. It's not just automatically assigned to a group. You could go through the list. You can understand whether you like to work more or work less, and take the presentation topic. At other times in this course, like 5 years ago, we wanted to make student presentations kind of accessible to everybody. However, which I think it's not such a bad idea, but we have to stop it owing to overwhelming negative feedback from students. Right, that's because the presentation, irrespective of its quality, is about a certain topic, rather narrow one. And it's difficult to learn something from the presentation. And students usually have delusions that they have to learn something at university, right? So when we made these presentations open to everybody, students attended them, and that resulted in negative reactions. So we have to stop this, which I guess it's a bit of pity. It's pity. So now presentations are only accessible for members of the groups which present. And the slides of the presentations after some time are accessible for everybody at right space. More questions? The mask. I shall ask questions. So, how did you experience the homework? Was it difficult, too difficult, too easy? Whatever the opinions, I would like to hear them. Was suitable. The difficulty of the homework was just right for me, not too difficult. Very difficult was right. Like it could have one or two similar parts in previous PSS. Andrew, could you please elaborate? Can you write your reaction in more detail? I'm not quite getting what. Right, Lucas. Yes, indeed, exercise 3 is more difficult because first you just, to warm you up a bit, right? Exercise 3 is more like actual exam problem. So it's supposed to be so. But anyway, it's important to understand that all these problems, starting from 3, they have essentially the same structure. There is a Hamiltonian, there is some perturbation, and you do perturbation theory. For that, you need to understand what are states which are obtained by action of elements of perturbation Hamiltonian onto ground state, right? And compute matrix elements and this in the basis of the states. Substitute these matrix elements. We've been talking about the energy corrections later. In the second part of the course, we'll talk about decay rates, and there you need these matrix elements for golden Fermi rule, but it is more or less the same scheme. All right, from Andrew. Solve a similar level of complexity, if not the same problem, might have been useful in a previous session. I would say that all further problems will have the same level of complexity as problem 3. So that will be all right. You will change around this complexity enough. Is it possible that we have more problems for proof instead of calculation? I thought I understood the problem, but due to calculation mistakes, I didn't obtain the correct answer. No, Yunzai, it's not possible. The kind of pedagogical goal of this course is to teach you how to do calculations. So not, rocket science, not really challenging. Yeah, but still it is at the level of advanced quantum mechanics. So we don't train much theory, although of course theoretical element is present. In homework, we train operational skills. Given a problem, go through a set of steps, get the answer. So I'm afraid that it would, if we do it otherwise, our pedagogical goals won't be reached. Let's see. When the second homework will be online. I have to look at the lecture schedule. Usually I try to synchronize it with lectures. Perhaps it's already time for this. Anyway, the deadline for second package somewhere in infinity, I believe it's beginning of May, something like that. All right, I will perhaps release it these days. Question from Isaac. Other presentation assignments also on exam level? There's not to be compared. Exam consists of two parts. One is a problem to solve, right? So you need to show off your operational skills. The problem is pretty much standard, and it is solved in a certain way, this perturbation theory usually, right? And you're very much guided along the way, just two operational skills. The presentations are, as I say, very various. The actual problems, calculation problems arise during presentations differ very much from presentation to presentation in complexity level and also in the level of techniques. That's why they're not intended, for something which you can write a report, which you can exam for. It is just to show that you can solve a little bit in a problem in a various context, in a varying context. Is it clear? Because this is a kind of important point to understand about the course.
Yes, it's clear. Thank you.
We can give the correct answer in the problem description so that we can check if we are on the right track. In fact, there are hints, very extensive hints, which would normally prevent calculation mistakes. For instance, the problem 3, the form of integral is given, right? The form of answer is given. What you have to do is to compute the coefficient correctly. I would say it's the same as to give correct answer. Apart from the first exercise, I thought it was quite easy content-wise. I thought the biggest difficulty were ambiguities in the questions formulations. Some clear sub and superscripts, for example, would help. For instance, to clearly show that the second perturbation has a zeroth energy term in the denominator. Eh? I'm sorry, Sasha, but that you're supposed to know from whatever elementary quantum mechanics perturbation theory.
Yeah, of course. I also said it was clear content-wise, but like in the question, you have. I thought in question 3 there was calculate a second order correction, then you have just energy denominator. While normally, if one writes down the formula, he has energy with 0 in a superscript. So then it's like these small things. Okay. And there are a couple of those that it's not clear whether you want the 0th energy or the first energy.
These extra indices just make me slightly dizzy. I don't know where to work, where to look at, but this is a bit subjective. Also, yes, about ambiguities in indices, that one. A part of operational knowledge that one has to understand that there is no kind of the system of indexing, the system of notations, which is commonly accepted throughout the world from Japan to Alaska and back. There's no such system of notation. That's why it would be very sad if you are trained in a certain system of notations, and if somebody would change the notations, you would be lost. So it's also a bit intentional that we use a little bit different indices, and it's a part of your effort to understand what is correct for this problem. Well, it looks quite close, Andrew, but in fact, it's about the same distance as from Japan to Europe. Yeah, because we are in Europe, we're Europe-centric, and distances in Europe look large. While the rest of the globe kind of is projected to the same point. Will all next problems will be exam difficulty? It is, yeah, yes, Eric. One shouldn't say it's difficult, but they will be structured as exam problems. Although it also vary a bit from problem to problem. Yeah, Nayan, what did you find difficult in homework? I know that you're a good student, and I kind of that's why I'm asking. Nayan, are you here? So, what did you find difficult? Can you formulate it, or was it? If it is unusual, if it was difficult because it was unusual, it's fine. But if there's anything else, I'd like to hear it. Sure. Any other questions? Notations in question. Sorry. Like the same as Sasha mentioned, there were too many energies, something like that. Alpha, beta, yeah, okay. That alpha, beta, vector k that has been defined, has been suggested to you. So it's, yeah, that was the task. That was something to do. So kind of half of the problem which you do is really algebra. You transform things mathematically. Another half, which is in principle easy, if you feel the problem, if you understand what to do, is understanding what formulas to write, for which states, which matrix elements have to be computed, what is happening with a state if you apply certain combination of creation and annihilation operators. So that these C dagger, B dagger, with K, without K are not abstract mathematical symbols for you. They're not. They really do something with particles. They create, annihilate it, and you need to develop some feeling for that. William, it's no lecture, it's a problem-solving session today. Perhaps you've been late. The lecture will be on Monday. We're no problem-solving session, and I just answering arbitrary questions about the course. Yes, Nayan, I understand, but that's also not difficult. That's something to learn to practice with annihilation creation operators. So it's not, you cannot reduce the problem just to algebraic exercise when you make algebraic transformations and get the answer. And that part we actually wanted to make as easy as possible. So one need to develop some feeling for this, what is happening with the quantum state, with the quantum states. But anyway, I guess during the further packages, you will get more practice and it won't be difficult anymore. No, there will be no problem solved during the session. Just Krista managed to make a compact presentation, so we are happy with this. It's also kind of almost the last meeting in this half of the semester. I would like to receive some feedback. Partially, I have received this when I ask about homework. We could just put feedback more explicitly, whether you like this course, what you dislike, what you don't like. I just want to suggest not saying something is not difficult. This is very subjective, and some people can still find things difficult if you think it is easy. Yes, in this, but if I would say it is difficult, I would be lying to you, right? And first, kind of thing the teacher should avoid is lying. One could trick students, but I prefer not to lie. Things which you learn are not difficult. They might seem difficult to you because of different problems, because you didn't think much about this, or you had a background which somehow is not good. But these things are not difficult, definitely. And I wouldn't lie. There are examples. I don't know whether it would serve to your encouragement or to your perhaps even intimidation. Like students like 30 years ago, they've been very different from your generation. During no internet, information was not that readily available. And it was also so that students, partially owing to that, partially owing to different circumstances of social life, were much less self-confident. You know how this mechanism works. You could Google something, you get some knowledge, you can whatever reply it, whatever, you got encouragement. 30 years ago, people were not that ready to get this encouragement. Students would be less confident. They would rely less on their own skills. However, you remember the lecture on magnetism. Who remembers the lecture on magnetism? Am I doing so bad? You do, very good. Sure, there was a lecture about magnetism, and first half of the lecture basically estimated kinetic energy, Fock energy, Hartree energy, and derive minimization equation. 30 years ago, that part of the lecture was given as an exam problem. For students which were less confident and less prepared for complex exercises, unusual exercises. Our lecture about superconductivity. A third of the calculation which I did during the lecture was also given as an exam problem 30 years ago. Like the wave function which I kind of motivated and wrote for superconductor was just given, and something about this wave function had to be computed. Right. Sir, again, Yanis, I'm sorry for that. I understand that it's not very politically correct to say say something which might be an indication of the level of difficulty which you experience. Okay, but again, let me state it again. The topics which we study in the course and the manner with which we approach these topics is not difficult. Question from Nayan. So you would say that the level of examination has gone down? No, it doesn't make sense to compare the examination of that time with examination of now, because also the pedagogical problems, the structure of the course has been difficult. And such, I didn't mention, of course, this explicitly. 30 years ago, I was not given this course. It was given by a professor who's gone now. It is okay. The good estimation of the level of difficulty of the exam is just how much students pass it from first round. I would say that these exams of 30 years ago had passing rate about little bit more than 50%. But that time students actually had almost infinite possibility to for rehearsals. Now it is limited. Now I guess last time the in Dutch it is called slagpercentage. So the fraction of people who have passed exam from the first time, I guess last time it was 66%. Sure, I would say that the level of examination for adjusted to student level stays about the same, a little bit easy. But students have been different, as I said. They lack self-confidence, but they had more extensive skills, I would say. They were less informed, but they had to rely on something which they could not Google, which they have in their hand, their mind. Right. So they should have learned certain tricks and then be ready to apply these tricks at any circumstances. Kind of having Google in your own head. That was very different from what you experienced, but operational knowledge remains operational. You should be able to do something to make a certain number of steps just from your head without consulting Google. Are the solutions available for exercises in the book? Nor for exercises which are not explicitly solved in the book, nor solutions are available as kind of written material. Some authors actually earn money out of that. They put money exercises and themselves solutions separately. That's not what I do. So the policy of the book that difficult exercises, lengthy exercises are being solved explicitly, while less difficult exercises were left for self-solving. Good. Somebody, please give me more explicit feedback about the course. Difficult. Yeah, we understand. We understand already that the difficulty is personal issues. If you say it is difficult for you, I would be ready to hear that, and I would be glad to understand what do you find difficult. Because yeah, if the problem becomes concrete, it's usually not difficult to solve. Any remarks about structure, organization, things like that? I also welcome questions about physics. I like the book, the fact that the book matches very nicely with the lectures. The book helps a lot. Thank you, sir. I've been given this course for a number of years before I decided to write this book. And the second author is actually an instructor who was by that time PhD student at our university. So he's been helping me with this course for a number of years, and we wrote this book together. So it's in principle, it's very well adjusted to given a course in general and to this particular university. Fine. Good. I wonder if questions are exhausted. I would love some more. But I think they kind of mostly exhausted. Oh, there is. Are you currently doing any research? That's question to me. Yes, I'm currently doing research, of course. It's not the education is not the major part of my working time. I'm doing research in quantum transport. I give also a course of quantum transport, which is closer to my current research topics. Online teaching also doesn't help to see the average level of students. It has been 1 year. I didn't see a teacher in real life, I think. Did I see a real student for a year? No. Nevertheless, you know what, we actually regard each other at pretty abstract level. And if you, for instance, ask questions online, I perceive it more or less in the same way as in real life. But eventually I read faster than I listen to. That's why it's a little bit more efficient. Will the lecture that discusses the solutions of homework sets will be uploaded. You mean problem solving session, Elvis? It has been uploaded already. You can see it at the bright space. Yeah, there is a link to my YouTube, but I guess it's unlisted. So it's just a link, a private link, which you can find in announcements of the at the bright space. I think it would help in the course if a little more time would be dedicated to recovering the prior quantum knowledge. Yes. Look, Matteo, we have spent the whole lecture on this, and the whole problem solving session. So in total, that was about 5 hours. Yeah, at least 5 hours. What would you like to do more? 2 lectures and 2 problem-solving sessions. Suppose you're a teacher, what would be your solution? Repeat the derivations more in detail. You mean the derivations related to elementary quantum mechanics? Yeah. Correct me if I'm wrong. This derivation you ask for would not be really helpful for your operational skills, for instance, for passing examination. And you won't um, learn much if you go through derivation. I understand that if you ask for that because you want to be confident about perturbation theory. Kind of look at this perturbation theory, or I know that I know how to derive it. Do I read you correctly, or is there something different? Is there a different reason why did you ask for derivations? Mateo. Because if you think you need more derivations, and this is general, that's why I'm talking about many people ask for more derivations because they kind of lose the line. And they fear that they are not able to do these derivations by themselves. Yes, Sash, yes, it's a good idea. I will answer this question. Look, that's my hypothesis. I would like if somebody can kind of confirm that or disprove this. Students usually ask for more derivations when they feel they miss something, and that results in a kind of losing the confidence. All right, if this is the reason, there's very simple, but perhaps a little bit, how would say, obtrusive answer. But this is, unfortunately, again, correct and difficult answer. Do this derivation yourself. That's the only way to boost your self-confidence. Right? I would never have time. No teacher would have time to get all derivations in detail. Sure, at some stage, at some level, it's been assumed that students could do something by themselves, or at least follow the derivation without losing the feeling of confidence. Right? If there are problems with that, it is at the student side. Okay, one can say that a teacher underestimates level of the students and take something for granted which is not obvious for students. So there is a problem, but this is a problem of communication. In this case, teacher would appreciate if you really tell him what is this difficult. Is there a difficulty in notations, difficulty in algebraic procedure, difficulty in operational level? Everything can be done, but that needs some feedback from a student. Right. So I think it would be nice to have a platform on which we can ask questions about the exercises outside the supervised homework sessions. I know there is a Brightspace forum, but I have feeling that it's not really actively used. Yes, there is Brightspace forum. Unfortunately, and if you know the trick, I would really appreciate your technical help. Unfortunately, I don't get notifications about the messages posted in this forum. And I searched how to tell Brightspace that I like these notifications, but I couldn't find the solution. If I knew the solution, that indeed these forums would be very useful. I completely agree with Serchan. So, but yeah, it is. That's not. No, and it's very difficult questions about categorization of education. We are in a system, and I would not change to another platform because it's strongly, strongly, strongly discouraged. I know that some people, for instance, use discourse. Strictly speaking, it is illegal. That's how organization works. Or more precisely, it is not legal if a kind of teacher communicates with students privately, that nobody can forbid. It's not subject of any law. But yeah, even using the Zoom sessions could become illegal in a year. We're struggling for that. This is kind of organization, and the drawback of the organization is that everything is solved at very centralized level. For instance, I found the Brightspace a very bad platform. For instance, I could never find a good page with a simple scrolling with going through menus. It's very incomprehensive system, but it's been chosen by TU Delft. It's been bought. People buying for that, and right, it's I have to use it. Eric, you said you can. One, you can. If you would inform me what I can, I would appreciate. Okay, I guess we could ask the people. Okay, I see. Thank you, Eric. So I would make a subforum and simultaneously subscribe to this. All right, good. I will during the break, I will take an effort to see that. And if I kind of succeed, if I get success, I will post an announcement about my success, and we will use these forums very actively. Because what happens now, I don't get notifications, so I would see a message in a forum like in a month or so. Yes. Yes, Andrea, I would do so. Let us see. I guess I missed the question. Okay. Yeah, I wanted to reply to Nayan. I guess we could ask the people who make these rules to change them. No, I'm sorry, it doesn't work this way. People who make rules, they do not make these rules for other people to change these rules. Definitely not. The rules can be not convenient or even stupid, right? It's like a curfew which is imposed now. Perhaps we can ask them to suspend curfew. I'm not sure that it will work immediately. Okay, good. But I need to check whether it goes to my email or somewhere. It's also difficult because, yeah, I got like 150 emails per day. I would prefer to see it in some. But anyway, that can be sorted as far as notifications are sent. Good, ladies and gentlemen, thank you for your input. We didn't talk much about physics, but yeah, I do receive quite some suggestions, and I believe I could explain something about the course. Sure. Thank you. So we will see each other on Monday morning. There will be a section about quantization. There will be last lecture before the break. So with this, I conclude this meeting. Thank you for your attendance.